name is Kayla, and welcome back to Meteorology Monday. So yesterday, I was being real productive, and I was going through my bookshelf and trying to clear out, any extra college things that I didn't need, and loose papers, and I didn't like this class, so throw that away type thing. You see, if you watched last week's video, I said save your notes, but after college, it doesn't matter, okay? So, I was going through all of my stuff, and I came across my old homework problems, and I said to myself, my goodness, this would be a really good Meteorology Monday. Let me embarrass myself trying to resolve some of my homework problems, So that is what I am here today to do, okay? I have got homeworks and paper and pencils that I thought were sharpened but actually are not sharpened, so we need to sharpen those first. And today we are going to solve some old homework problems or laugh and get embarrassed at the fact that I can't do them anymore. First things first though, we sharpen the pencils. Technical difficulties. Good enough. Now we also have something else today. We have a second camera angle. So, let's go over to that one. Wave hi, hello, camera here. So, let's go to, look at that. Got a 50 out of 50 on this one. Oh, A+ student. This is not looking good already. Upon further inspection, we're not doing that one because I have no idea how to do any of those. 1 point, old homeworks, 0 points for Kayla. This seems a bit easier. This has to do with jet streaks. Alright, so we are starting off with one of my homeworks on jet streaks from the class Kinematics and Dynamics. Kinematics and Dynamics was not the funnest course in the world. It might even be one of the harder courses in meteorology, unless you have a good teacher. That might change things. If you're not in kinematics and dynamics, you might not have any idea what this is, but that's okay, because I might not either. We'll see. But this is a problem that I did so many times over and over and over my last 2 years in college. So, I should be able to do this one. I think I can do this one, okay? So we're gonna switch over to the other camera angle, and I'm going to write out the table. So in this case, we have a jet streak right here, and it is slower here and slower here, so it's speeding up and then slowing back down. Slower up here than it is in our main streak, and it's slower down here than it is as well. We have our 4 quadrants, A, B, C, D, and our basic north, south, east, west, x, y, yada yada. Now, from this diagram of a jet streak, we are going to determine, or I guess I am going to determine, the relative vorticity, the planetary vorticity, the relative vorticity advection, the planetary vorticity advection, the divergence, and the vertical motion, also known as omega, for each of these quadrants. Thankfully, I do not have to find numerical values. I'm just assigning a sign to each of these, so either positive, negative, or 0. Shouldn't be too hard. I have 3 options. So relative vorticity, let's see. I know this has a lot of circles. You do a lot of circles. And I'm not gonna cheat.
So let's see, relative vorticity. Relative vorticity would be the vorticity at each place. So that means if it's fastest on this, yada yada, there's a smaller arrow that goes there, a small arrow that goes there, because the wind is moving slower here.
So let me explain why this is relevant also, so that you're not just thinking this is like a made-up problem. This is like an example of a piece of the jet stream. So everybody knows what the jet stream is, right? We all know what the jet stream is. So this is a little piece of it. So we're finding out how air moves and sinks and rises and goes left and right around a jet streak. So relative vorticity in A, since it's going faster down here and slower up there, then kind of like a fast car passing a slower car, the air around A is going to want to go counterclockwise. Let's do same thing here, opposite here, fast, slow, we're just gonna draw circles, okay? Those are, yep, looks good so far. Counterclockwise is represented by positive, clockwise is represented by negative, due to mathy stuff. Yep. So, relative vorticity here is positive, positive, clockwise is negative, negative. Done. Good to go. Boom. I got one row. Alright. Planetary vorticity is something different. This has to do with the way the Earth moves, I think. If I remember correctly, planetary vorticity is based on the hemisphere. And if this is in the northern hemisphere, everything will be positive. And if this is in the southern hemisphere, everything will be negative. So, always assuming the northern hemisphere, because we live in the northern hemisphere. If you're from the southern hemisphere, I'm sorry, this example is not for your weather. So northern hemisphere, we will put positives, 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 positives. This has to do with something that I don't remember. I just always remember writing a positive there. So, relative vorticity advection. This is which relative vorticity is coming into A lot of you are going to be in meteorology school right now looking at this and knowing exactly how to solve this and laughing at me because I can't remember. And a lot of you will have no idea what I'm doing, so it makes me feel better. So I can say whatever I want right now and half of you will believe it and half of you will see right through my lies.
Relative vorticity advection. Let's go from A. The air from A is moving into B. There's positive here, there's positive there.
Yeah, I have no idea. Planetary vorticity advection. Since all of these are plus signs, nothing's changing from a positive to a negative, so this is all zero. Divergence. Divergence would be what's happening above this. So divergence is the opposite relative vorticity, which means negative, negative, positive, positive. Vertical motion. This is like we have a low pressure here, low pressure there, high pressure, high pressure. So if it's going, we call this, okay, I'm going to show you a trick. You're going to be real impressed, okay? This is something that we call the right-hand rule, okay? Watch this, blow your minds, okay? We look at this, it's going counterclockwise. So we take our 4 fingers here, you know, put them here, and we're going to curl them in the direction that you see the little spinny thing. I'm going to curl my fingers in that direction. My thumb is pointing up, so there's rising motion. So that's a positive for A. Same thing for B. Curl my fingers, thumb is pointing up, rising motion. Opposite here, fingers curl this way, thumb is going down, negative motion, which is sinking. So, boom! The only thing I don't know is relative vorticity advection. So I'm just going to leave that blank. Now let's check to see if my answers are correct. Relative vorticity, positive, positive, negative, negative. Boom, got that. Awesome. Did great. Planetary vorticity, I remembered that, you know, northern hemisphere, all positive, 2 for 2, doing great. Planetary vorticity advection is all 0 because positives, positives, nothing is changing to a negative. So everything is 0, everything is 0, boom, got that one. I am a genius. Look at this, I remember this. This is 2 years after graduating, but not 2 years after taking the course. So, I have officially been graduated for 2.5 years. I took this junior year, so it's been like 3.5 years since I did this. Divergence. This is where things start going badly. Divergence is wrong. Vertical motion. Why is that wrong? I feel like that's not wrong. I feel like this is actually right, you know? Why would this be wrong? Oh my gosh. Guys, I've made a mistake that one should not make after going through synoptics 1 and 2. So that right hand rule, you know, that I showed you, my fancy little trick, that's for relative vorticity, not vertical motion. Let's erase this, because I know how to do this one, so I'm going to redo it, okay? And I'm going to give myself a point for it. Vertical motion has to do with the region of the jet, alright? You don't care about any of the information I'm about to say, so hit fast forward.
So when we took it, we had something like this. So we have this way, we have a left and a right, and we have an entrance and an exit. So this right here would be the right side entrance, and over here would
I'm actually really proud of that one, okay? I remembered something. Goodness, oh my gosh. During school, you have no idea. I did these so many times. Literally everything, like every week's homework, I'm not kidding, like looked like this. There was 1,000,005 of these that we had to do. The fact that it took me this long to remember how to do those last two is kind of sad with how many times I did it, but like I said, it has been quite a few years. So, when people ask, do you ever use that math that you learned in school after you graduate? Will you ever use it in your real life? Is there any job out there where you would have to use this? I did not imagine YouTube being the place that I would use it, but here we are. So this is the part of the show where I admit my defeat and say that I was really planning on doing a senior level problem, you know, from Synoptic 1 or 2 or physical meteorology or something like that. But let me tell you, I have just sat here for the past 15 minutes looking over my homeworks and such, trying to find a problem that I think I could possibly do. And I have not found one. I am giving the heck up, okay? I cannot do this. I don't know what any of this means anymore. I am kind of wishing that right out of school I had started looking over my notes immediately and trying to remember these things, because as much as it was like a pain to do in the moment and stuff, it kind of feels sad not being able to do these problems anymore. And I really wish that I had stayed with it and had kept going over my notes and stuff even after graduation. Because I'm looking at these problems and I'm seeing what I did and I'm like, oh my gosh, I remember doing them, but I don't remember why I did half the things that I did. In all honesty, if you're currently a meteorology major and you're going through all these classes right now and doing all this math every single day, unless you're going into a research field or you're doing a silly YouTube video like this in like 4 years, you are probably not going to use all of this math. I get that question asked a lot. Will I use this math when I'm done? Do I have to remember everything? You don't. For those of you in kinematics, you'll probably also never have to use the planetary vorticity advection again, although you know now that the answer is always 0, so hey, helping you out. Math like this, if you're someone like me, is always fun to keep up on. Highly encourage you fresh graduates to definitely look over your notes a little bit more than I had, instead of stuffing them in a box or the back corner of your bookshelf. For those of you in school, hopefully this encourages you to, you know, get through the class and then you can forget the stuff and not have to worry about it again. Unless you are research, in which case remember your stuff. General forecast or broadcast or something like that, you don't need to know any of this after graduation. Hopefully some of you guys found this entertaining. I had a lot of fun doing it. It was cool to look over all of my old homeworks again and try to find a problem that I could do unsuccessfully. But as always, you can follow our weather adventures over on Instagram and Facebook. The links to our blog and Patreon are still in that description as always. Go over there and check out our Tech Thursdays or check out our Patreon to see behind the scenes footage and pictures of our chase days. Until next time, I'm Kayla. Thanks for watching and happy remembering that right hand rule. See, look, a thumbs up is a positive relative vorticity right here. This is too nerdy, I've gone too far.